All right, so we're more than halfway through this class, coming to the end. Today we're going to talk about storage and memory and then demonstrate some assembly projects, including the new ARM assembly coding, which students have been asking for, and I was very glad to get it working. So let's start with the textbook stuff, which should be here. All right. All right, I'll have to, my slides. I'm catching on. All right, there we are. That's what I wanted. I made slides out of these things. There we go. So, all right, and we're just following the book. All right, so we're going to talk about the types of memory you have and a whole lot about caching and how caching works. So I've got, you can demonstrate the consequences of timing here, and I've got this ready to go. Let me make this bigger. This is my, running on this Mac, a virtual machine in VMware running Debian Linux. And as you can see, if I do uname -a, you can see I'm running 64-bit ARM architecture. You can see that here too. So that's what we want. And for this demonstration, it'd be fine if you used Intel too. It doesn't really matter. Later on, it's going to matter that I'm using ARM. So if I look at this, I've got two things here called average mat. And if I look at the source code, average mat v1.c. All right, this one here. Now what this thing does, let's see if I can, there we are. It allocates some space down here for something that is n integers, and then it makes a matrix of n rows of n integers. So it makes a two-dimensional array of data, n by n, and n is 30,000. So it's pretty big. And then here, it just says for I and j going through then it just adds up all the data in all those locations. And so notice I and j are like this in this one. And so I can probably just do head minus n15 average mat1.c. And then I can do the same for average mat2. So we can compare them. And the only difference is here I index by I and j, and here I index it by j and I. So they're both going to do exactly the same calculation. They're going to add all these numbers. The difference is this one is going to increment the second index first, and this one is going to increment the first index first. And so what that means is one of them is going to load contiguous data items that are right in a row stored in memory, and the other is going to keep jumping by 30,000 and then do again jumping by 30,000. And as you might imagine, that changes the efficiency. If you run these, average mat1, on this processor that took about 0.9 seconds, but the other one, 2, you can already tell it's taking quite a bit longer. It takes 8 seconds, 10 times longer. So that's the point. So doing the same addition on the same numbers, but accessing them in a different order, greatly changes the efficiency of your calculation. And when I did it on my old Intel processor, one of them took 10 seconds and the other took 2 seconds. So the difference is, anyway, one of them is a whole lot slower, and that's the point. So there's different places to store data. You can store it in the registers right on the processor, and that's the fastest, but there's not very much of that. There's caches available, which are much bigger, but somewhat slower, and then main memory is a whole lot slower again. That's RAM. And then, of course, there's the hard disk and the SSD and all that stuff, and storing things far away on the network that are much, much slower. So level 1 cache is close to the arithmetic logic unit. Level 2 is slower, and level 3 is used to share data between cores in a multi-core CPU. And then there's storage devices, of course. Primary storage is the registers and RAM. Registers are much faster. Secondary storage cannot be directly accessed by the CPU. It's going to have to run code to fetch the data from them and put it in RAM and then read it from RAM. And that's how the hard disk and the floppy disk and the SSD and everything work. So you consider your criteria. Capacity, latency, and transfer rate are the main things that determine storage. Capacity is how much data you can store. Latency is how long it takes to fetch data, and transfer rate is how much data per second comes through once you've established a connection. So primary storage, RAM, they talk about this. Your registers typically have 48 bytes, but it's only a nanosecond. Your cache is a few megs for 5 nanoseconds, and your main memory is 100 nanoseconds. And you, of course, these days have 4 gigs or 8 gigs or 32 gigs or something like that of main memory. All right, and so you can see the cache if you want to with LSCPU, and you'll see how much cache you have. Here was, I think, my old Intel machine's cache, and my new one has somewhat different amounts. But anyway, you can see there's level 1, D and I. I'm not quite sure what the difference is, 32K each. Then level 2 has 256K, and level 3 has 12 meg. So there's various caches available. All right. And then secondary storage, flash disk, hard disk, and remote server. The flash disk is by far the fastest, also more expensive, and it uses less power. And of course, almost everything is using SSDs now, phones and portable machines like the MacBook Air and everything. All right, and so you've got the CPU has got the arithmetic logic unit on it and registers right here. Then the cache is a little further away and a little bit slower. Then there's the memory bus to get you to the RAM, which is where you have most of your working memory. And then you have your I/O controller that can fetch data from these remote devices like the hard drive and put it in RAM. Again, much, much slower. All right, so you consider locality, which is how close are two data items to each other. And temporal locality means a data item has been used and then you use the same one again close in time. And spatial locality means it's at a similar address. All right, so that's temporal locality. And so in this program here, I have a loop for I equals 0, I less than n, add something. So I is going to keep being accessed every time you do this loop. It's going to make several references to I to measure it. Then it's going to spatial locality will consider these elements of the array, and it's going in order: array 0, array 1, array 2. So those are spatially nearby. All right. Now the point is, modern systems don't load one block of data from a cache. Don't load 1 byte of data or 1 word of data. They load a lot of data at once, typically 16-byte block size, something like that. So that's why it was much more efficient to access these in order, because you're going to load them 4 at a time anyway. So, like I say, this one loads elements in order. We already looked at this one. This one loads them out of order, and that makes it much slower. All right, let's take a look at a Kahoot, which I've got ready here. Let me bring it down here where you can see it. And it is 11A, which is here. There we go. All right. We'll start here and see how it goes. All right. All right. What memory has the highest cost per byte? All right, the registers are the fastest and most expensive. All right, I got an echo, which I don't know how to get around here. Anyway. All right, what cache shares data between CPU cores? That's level 3. All right, what's on the CPU chip? All right, and that's the registers. Okay. Okay, so let's get back to the slides. There they are. Okay, so now let's talk about caching, which can get a little confusing. So the computer needs to store data in this limited amount of cache. You don't have enough cache to cache everything in memory, not even close. So you're going to have these little bits of cache that keep on refreshing with data you seem to be using, and the computer will have to constantly decide whether the data it needs is already in the cache or whether it has to refresh the data in the cache. So a cache hit is when you look for the data in the cache and you find it there, so it doesn't bother going to the memory. A cache miss means you're going to have to load the cache from main memory. All right, so that's called cache eviction. If you look for memory and you go to the cache and the memory there doesn't contain what you need, then you evict what's currently in the cache, that piece of cache, and load data from RAM. The cache is often full, of course, because you keep loading data in and you only remove data when you have to, so it's full to be used. So that there's 3 cache designs: direct map, fully associative, and set associative. Now, direct map is where you divide the cache into cache lines. Each line is independent, and it's got a data block and metadata. And the data block is a block of program data from main memory, typically 16 to 64 bytes, and metadata is information that tells you what piece of RAM this is. So it looks like this. You have, say, if you had 4 lines of cache, then you would probably just put them in order. So the first, each one of them can store 32 bytes, looks like. This is hex. So it's every block of 32 bytes maps to one, and you put them in order, then in order, and then in order. So all the pink ones could be stored in line 0, and all the yellow ones could be stored in line 1, and so on. This is one way to do it. And so now when you request memory, the lower bytes of the address will identify where it would be within a line. Some bytes in the middle will determine which stripe it is, which line. All right, and that's game here. All you need is to take a few bytes out of the middle of the address to determine which one of these cache lines it maps to in a direct mapped cache. All right, so the metadata is going to have to tell you, does it hold any actual memory? 1, if it does. If so, which of the many subsets of memory that map does it currently hold? And that's going to be the tag, which is going to be the higher order bits of RAM that determine which one of these blocks we're in. So that's what it holds. And so the tag tells you the higher order bits of memory here, the index tells you the middle order bits, and the lower order bits tell you which bytes within this block of maybe 32 bytes you're talking to. So that's how it works. And so that's, like I said, the offset here tells you which block you are inside the line, the index tells you which line, and the tag tells you which part of memory is currently stored here. And the valid bit tells you whether it does contain valid data from memory or not. So that's the index portion, uniquely identifies a line, and the offset port uniquely identifies a byte within that line. So if you have a CPU with 16-bit memory addresses and 128 cache lines, and 32 bytes of data in each block, then if you did the first read and the cache is empty, then of course it will have to be a miss. It will go here and it's not going to find the data is already there because we just turned on the computer, so there's nothing in the cache, or for some reason the cache is empty. Even turning on a computer wouldn't cause that in reality, but we're going to start from such a case. So it will load from memory. It will go load from memory location 1010 and load it here, and we're going to mark that as valid because it does have a valid copy of the contents of memory. Now the next time we read, we're going to read something inside that block. 1010 and 11 is the same tag and the same index, so it's included in the data that was loaded here. So when you try to read something else very near the previous byte, it'll find it in the cache and you're fine. You don't have to go to main memory. You can save a lot of time. Then when you try to read here with a different tag, 1001, and an index, then you're going to have to load this stripe, this line, because you never used it yet. So this is going to be the same as before. It's going to find no valid data in there, so it's going to fetch the data and load it up. Then when you try to read from this one down here, you're going to read from something with an index of 3 but a different tag, so it's going to go to this line and find that it is valid, but it's from the wrong part of memory. So now it's going to have to do a cache miss. It's going to have to clean this stuff out and load in new data from memory and fill it over. So that's going to take some time. All right, so now if you're going to write to cache data, we've only been talking about reads here, but suppose I'm here where I did a hit. I was going to write to this, so I already loaded this block before, now I'm going to write to it. So the question is, do I change the data just in the cache, or do I change it in the cache and also in main memory? And so there are different techniques. One is write through cache, where you always update them both simultaneously. That's going to take a lot of time, though. The alternative is write back, where you modify the value in the cache data block, but you don't update main memory. So now you're going to have another status bit, a dirty bit, to record the fact that the cache data is different than main memory. And you're going to have to remember to sooner or later write it back to main memory, or the main memory is not going to be accurate. So that's the dirty bit you add as addition to the valid bit, and that's more complex, but of course it's going to save you a lot of time. Especially if you keep writing to the same location in memory, you can do writing just to the cache, which is, like we say, something like 100 times faster or 10 times faster than writing to main memory. So you save a lot of time that way. So here's direct mapped write. This is with write back. So when you write to this location, it finds that it's cached, so it's going to change the data only here and then mark the dirty bit, so that you know that the data in this cache is more up to date than the data in main memory. All right, and so the write is valid, but the tag doesn't match. So when you try to write to a different tag here, then you're going to know I need to save this data to memory. I can't just throw it away and load data from memory. I'm going to have to do a write to memory and then a load from memory because the dirty bit was set. All right. So cache misses, cold start misses are the ones we talked about here. If there's nothing in the cache at all, then obviously you're going to miss everything. You're never going to find anything in the cache. You'll have to load things. And then capacity misses are going to happen when the cache is full. So you can't find any more room in the cache, and therefore you have to load it. And then, of course, conflict misses is when two frequently used variables map to the same cache location. If that were to happen, if we were to have two things going to the same cache stripe with different tags here that we keep writing to over and over, we're going to keep on having to vacate the data from the cache and load it again, and that's going to be very inefficient. All right. So an alternative is an associative cache, where you don't have each block, each line of cache forced to only store certain memory locations that can never change. Are these misses noticeable to the user? Delayed action. Yeah, you won't notice them individually because it's a small fraction of a second, a few nanoseconds. What you will notice is your machine running slowly. Like we just saw, that program that could run in 1 second, in fact, takes 10 seconds to run because of all those cache misses. So that's all. Your things will be slow and irritating, which is what you see when your RAM gets full, as you probably noticed. So fully associative is where you let every memory region occupy any cache location. So that's the maximum flexibility, but now it's going to be higher cost to look up and evict data. every time you try to read or write to the cache, you're going to have to hunt through the whole cache to see where the memory is. Now back here, we had a one-to-one mapping. We get back to this picture. Back here, we had a real clear one-to-one mapping. If you wanted some memory here, we knew what cache line to look in, and it would have to be there and nothing else. But now that we're going to let any data be stored in any cache line, you're going to have to hunt through the whole cache to see if your data is in there every time you read or write. So that's an issue. All right, and that's the fully associative memory. So this might be useful for some specialized things, but in general, this is too inefficient for use in a general purpose CPU. So what you typically have is the set associative one. This is a middle ground. And so every memory region maps to one cache set, but each set stores multiple lines, so we have more chance to store more data there. So instead of having one index point to one line, we have multiple cache storages in this line. So if there were two different tags with the same index that we keep referring to, we could store them both and not have to keep refreshing the contents of the cache. So this, is the obvious sort of middle ground. That does mean, of course, every time you read or write, you're going to have to check both of these blocks within the cache to see if either one of them has the data you want. But you can do that in parallel if you design this in hardware. And remember, this stuff is in hardware in the CPU. You can arrange logic gates that simultaneously probe both of these to see if it's matching this index data. So this won't cost any time. And that's the idea. So it uses the least. So when you decide to evict data, you'll have to figure out which one of these to throw away. If you look in the line and both of them don't contain the data you need to throw one away. So it keeps track of that with the least recently used line. Whichever one you have not used recently is the one it throws out to make room for the new one, which, makes sense. That's presumably the one that's less important. All right, so you got the same kind of setup here. We're going to set up least recently used. 0 indicates the left was most recently used, and 1 means the right was most recently used. So here we got a cache. We got 2 blocks of data storage in each line. We have a mark to see which one of them was least recently used. We have a valid bit and we have a dirty bit. So we start going into a cache that's never been used, so everything is empty, and we're going to do a read from this location. So we'll go to that line, and of course it will have a cache miss. The data is not there, so it will load a block of data and fill it up. And now this will be the other one will be marked least recently used, and this one will be marked valid. All right. So then we're going to do another read from it, and in this case we got 103. So we're reading from the same block of data, so we're going to find the data right here. That's going to be a hit, and we don't have to change anything. Okay. Then we're going to do a read from here with a different index. So that's again going to find empty data in the cache. So it's going to load some data from memory and fill it up and use that. Then we're going to read from here with a different tag. So we're going to go here, find that there is some data in the cache, but the tag doesn't match. This one is empty, so it'll load data over here. So now we have 2 blocks of data loaded at the same line of cache. This is the benefit of this model we're using, the set associative. We have a set of things in one line. All right. And now we're going to write to this address, which is 1110. And this one, so we're going to write to one of these. So now it's going to write here. It's not going to update memory. Instead, it's going to mark the dirty bit, reminding it to eventually put this stuff in memory later. So if this keeps changing, we can just keep changing it in the cache, which is fast. All right. And then we have another write to a different address, which is going to be 10100. Here it's going to be writing on this side, so that's going to make this one dirty also. And so they both have the dirty bit flagged, and we haven't had to do any of those write operations to main memory yet. They'll happen later. Eventually we are going to have to write to memory, but we might be able to do multiple writes, reads and writes to this block before we do that, and that'll make the program faster. If the data is spatially close and temporally close. If we're doing something like running a loop, like updating I equals 1, I equals 2, I equals 3, then we'll want to keep doing writes to this without wasting time to get to main memory. All right, so you can analyze these things, and I did this, if you shrink them to 1,000 by 1,000 and then run them, they're much, much faster. This is matrix 1 and matrix 2. They're the same programs. So let me clear, make this bigger. All right, and then make it bigger, I say. All right, and then run matrix 1 and matrix 2. So they're much smaller and faster, but as you can see, one is much faster than the other, 3 milliseconds as opposed to 7.6 milliseconds. All right. And now I just made them smaller so valgrind can dig through it. Here's what valgrind does. This is going to run the program and analyze how many cache misses and cache hits there are. So here's one of it running, cache grind. And so you notice here I have misses 66,000. But if I run the other one, matrix 2, and that was L1 misses, 66,000. Now my L1 misses are, all right, D1 misses were 66,000, and D1 misses are now 1 million. So that's the point. By accessing the indexes in the array out of order, I made tons and tons of unnecessary misses. So that's why it's much, much slower. Like we saw, it's twice as slow in this case, twice as long. All right. So, and then you can talk about multi-core processors. To make it even more complicated, modern processors have many cores. This new Mac I'm using, I think it has 14 cores. So how you organize those so they actually get something done, I don't know, but this is part of it. So you have, here's 4 cores, each with their own level 1 cache, but a shared level 2 cache, and then you got memory bus. There's one way to do it. And so you're going to have, if 2 cores might have cached the same data and have different data in the same stripe here, then they're kind of contradicting each other. This is a problem with databases too, what I used to do decades ago. 2 people could try to write to the same address in a database at the same time, and you have to have, in that case, record locking. So in here they have a thing called a cache coherence protocol, ensuring that any core accessing a location always sees the most recently modified data instead of seeing an old copy. So here there are many, you have to have some system of making sure that none of those caches have data that's out of date when they're using it. So one way you do it is add 3 flags, a flag that says if it's been modified, a flag if it's been unmodified and can be shared, and if it's invalid. So you'll have to update these statuses of the block so you know whether that block's data has to be refreshed before you can use it. So on a read access, if it's in the modified or shareable state, then you can trust it. But if it's in the I state, which is what, inconsistent, invalid state, then you're out of date and you're going to have to load the new block before you can use it. That's the game. All right. And so same in a write operation, it's the same kind of issue. You have to decide whether if you're in the modified state, you can write to it. If it's in the I, which is invalid or shared state, then you're going to have to notify other cores that you're writing to it. Make sure everything gets up to date. So, that's the problem. There's a lot of more negotiating and arguing among the cores to make sure everything stays synchronized, but it's worth it because the cache is so much faster than main RAM that you end up saving time even though there is some overhead arguing among the cores. And so another way to, a snooping controller snoops on the bus for reads or writes. So it knows when people are reading, writing to blocks that it has cached, and there are other techniques, just ways to try to keep track of when the cache is changing. All right. Anyway, each core having its own separate level 1 cache is so much faster that it's worth all this extra arguing and negotiating between devices. You still save time. There's another problem of false sharing, where multiple threads are running simultaneously and accessing memory locations where they end up sharing things. There's another problem. You have to make sure that if multiple threads don't undo each other's work. And I know this happens in web applications. There are some interesting timing flaws in web applications where when a web app gets very busy, two users can end up sharing data and seeing each other's data. This has happened a few times, where it stores something in a temporary file and then comes back later to read it. And in that time, some other user's data has been stored in there. So there have been a few cases where somebody will log in and see a different person's Yahoo Mail or something from a thing like that. Anyway, that's what you have to mark. Keep track of things very carefully to avoid that. And one thing about this kind of flaw is that usually in a normal test, you won't see a problem because normal tests don't have a lot of users and a lot of load. So you'll test it, it'll pass your test cases, and then when you actually deploy it and it's used by a large number of users, there will be strange intermittent problems that you're not picking up in your test. Anyway, let's try another Kahoot. I should have those here. 11B, okay. All right. All right, so what happens when data from RAM needs to be cached, but the cache is full? Yep, you have eviction. That's interesting. Actually, miss is an interesting answer. It is technically a miss, but then comes an eviction. You could argue about the answer to this one. I say I wrote these, and sometimes they're not as clear. You're correct. This does happen. That also happens. I think I need to work on that question. I can't change the grading now. That's part of why these things are extra credit. Sometimes they're not as fair as they should be. It's a good point. Let me make a note. 11B. All right, I can fix that before I'm teaching this class next semester. I can fix that one then. Anyway, let's see if the next one's any better. So what does it mean when you have the valid bit set? Yeah, that's right. It means it contains valid data from memory. All right. All right. So what cache type is unfit for general purpose CPU? All right, in the book, they said the fully associative one has this property where you'd have to hunt through all the lines to find the data. That would be wasting too much time for a general purpose CPU. All right. Anyway, I see we had 5 players anyway, so there's a little bit of competition there. Anyway. Emmanuel, Adrian. Okay. And Izzy. All right. Fair enough. So let me stop this.